All right, I got 7:30. I'm just going to start with the order that I'm seeing on my screen. So we'll go with Keon first. Keon, you have a question?
Sorry, I didn't have a question. I was just here to review or
Okay.
see other, yeah.
Okay. Christian, you're next.
I didn't also. I was just here to mostly do review also.
Okay. Raghav? All right, Jezreel.
Currently looking, can you hear me?
I can hear you.
All right, cool. My thing's not turning green, but I'm looking through it. I'll get back to you in a bit.
Okay. All right, Jarek. Jarek, do you hear me? Got anything, or should I move on?
I just got here. You can move on.
Okay. Brenya. All right, so Brenya wants to do some implicit differentiation. And here's the equation she's giving. So tangent of x over y equals x plus y. And I am assuming at the very least we're looking for dy dx. Brenya, unless you want to do something different, that's where I'm going to take this. All right, so if that is the goal, how should we start? All right, so I'm going to take the derivative of this, of both sides of this equation with respect to x. So, and remember, when you're doing implicit differentiation, anytime you deal with, so we're differentiating with respect to x. So anytime we have to deal with a y term, we're going to be, that is going to necessitate a chain rule. So what is the derivative of the tangent function? That is secant squared of x over y. But then we have to find the derivative with respect to x of x over y. I'm going to leave that like that for now. We can deal with that in a second. By the way, it looks like most everyone is muted. If you have a question or if you have some input, go ahead and just unmute yourself or say something in chat. Otherwise, I'm gonna kind of keep pushing. All right, so left-hand side, derivative of that outer function is secant squared, keeping the input function intact, x over y. And then I also have to take the derivative of that x over y at some point. So I'll handle that in a bit. First, I'm going to take the derivative of the right-hand side. Derivative of x with respect to x is 1, and the derivative of y with respect to x is dy dx. So there's my kind of my first pass through here. I'm going to give myself some room because I want to deal with this derivative of x over y kind of on its own, just because I feel like it's complicated enough that it deserves that. So here we're going to need quotient rule. So this derivative is going to be equal to the derivative of x with respect to x times y minus x times the derivative of y all over y squared. So that comes out to be derivative of x is just x. So y minus x dy dx all over y squared. So from there, I can drop that into where I left off. So secant squared of x over y times y minus x dy dx over y squared equals 1 plus dy dx. Okay, I'm not seeing anything in the chat, so I'll keep going. From here, so remember our goal is to figure out an expression for this dy dx. So basically we got to get to a point where we can isolate that. I think the lot of ways to continue. What I would like to do right now is to multiply both sides by y squared. And what that'll help me do is to figure this fraction out. So that'll give me secant squared of x over y times y minus x dy dx equals y squared plus y squared dy dx.
Mr. Ruiz, I have a question real quick about
Sure.
on the like on the 3 lines in the middle where it says in parentheses y minus x dy dx over y squared. Is that just quotient rule?
Yeah, so over here on the right of this vertical line, that's what I was setting up over here.
Okay.
So yeah, if you treat x and y, so basically you can look at it this way: f of x equals x,
Mhm.
g of x equals y. And then yeah, basically this right here, to the right hand of the equal sign on that first line, that is me setting up a quotient rule.
Okay.
All right, so from there,
Sorry, why does it become, is that y squared plus y squared dy dx?
yeah, so I just distributed this y squared over here.
Oh, okay.
All right. Okay, I'll go ahead and distribute it on the left then. So I get y secant squared x over y minus x secant squared x over y dy dx equals y squared plus y squared dy dx. So I think I'm finally in a place where I can consolidate all my dy dx terms on the same side. So I will do that. Y squared dy dx plus x secant squared x over y dy dx equals y secant squared x over y minus y squared. So then I'll factor out a dy dx over here. And then I will just divide off. I will divide the left-hand side by the parentheses so I can isolate dy dx. And I'll get dy dx equals y secant squared x over y minus y squared over y squared plus x secant squared x over y. Any questions there?
Yeah, I had a question.
Sure.
On the rearranging of terms, like
Mhm.
after the line where it says secant squared x over y, I'm just really confused on how those terms got rearranged right there. Yeah.
Or can you see the pencil?
Yeah.
So from this line to this line, you have a question?
Yeah, like I'm just confused on how that became that on the bottom.
The only thing I did from this line to the one below it is that I distributed secant squared of x over y to both the terms in this bracket here. Or do we think I did that wrong? I think that's okay. And in terms of something else you mentioned was that you asked me how I rearranged those terms.
Yeah,
I mean, so for example, in this term here, you multiplying these three things together: x, secant squared of x over y, and dy dx. You can technically put those in any order you want. I just chose that kind of based on preference.
So it wouldn't matter on a test, like as long as all the correct terms are there, it wouldn't matter which
Yeah.
which one.
I mean, in general, ABC equals BCA equals C. I mean, really, if you're multiplying things together, I don't care about the order. So yeah, I do. That does not matter. I mean, there's a lot going on here where where I'm kind of rearranging things by personal preference. So for example, like this thing here, I could also say this is equal to, y squared minus y secant squared x over y over negative y squared minus x secant squared x over y. And this is kind of a common thing that happens when you're doing implicit differentiation. You can basically flip all the signs and get the same something equivalent. Essentially what I just did with these two things here, if you multiply either one of them by -1 over -1, you'll get the other. But one is not more correct than the other. So I mean, a lot of different ways to say something that's equivalent to the right answer. Anything else here? Okay, I will get a new page.
We go over a linear approximation.
Linear approximation. Yeah, you got an example for me?
No.
All right, so let's do let's approximate the function, the cube root of x. Around, I want to use this right here to approximate the cube root of 64.1. So if I want to approximate that, I have a function here. What do I need to do?
So this isn't just as simple as plugging in the 64.1 for the x.
No. So basically what the reason we're using linear approximation is that basically what we're trying to do is this, and I'll draw a picture. In the meantime, while I'm drawing this graph, Christian has suggested we take a derivative. So that absolutely is part of it. But basically what we're doing here is this. I have this cube root function, which looks something like this. So this is a deeply nonlinear function. But what I want to do with it is to approximate I want to find an approximation for the cube root of 64.1. And the way I'm going to do that is by basically taking a tangent line of this function at a carefully chosen value of x. So I think for most of the problems that I asked that I've assigned in this area, I give you what that x value is. But basically, if we're going to do a linear approximation, we need to find an x value where this approximation is going to be centered on. And what I mean by centered on is, so if you look at this graph here, I have a straight line, which is tangent to a curve. That straight line, so that straight line shares a location with the curve. So that point that I kind of bolded in here, that point is both on the line and the curve. What else do the line and curve have in common here? Not just that location, but what else?
The same slope.
At the same slope. I mean, that's why we're able to use this linear approximation. So one thing I kind of threw away was, what's a good logical x value to choose here to do this approximation with?
64.
64. I don't know the cube root of 64 or 64.1. I can much more easily figure out what the cube root of 64 is. So a while ago, Christian suggested we take a derivative. I agree with that. What is the derivative of the cube root of x? More importantly, is there something I should do to help me get there? Alexander says x, or 1/3 x to the negative 1/3. How do we feel about that?
Could probably simplify it more.
I think we're close, but I think that's actually not quite right. So remember, our function is x to the 1/3, right? Which means that the derivative will be 1/3 times x
to the negative 2/3.
Right. All right, so, and someone said we should simplify it a bit, which we can do. So I'll call this 1/3x to the 2/3, and that is our f prime. All right. Now, where do I go from here?
Do we input the x value of 64 now into the derivative?
Let's do that. So f prime of 64 is equal to 1/3 times 64 to the 2/3, which is equal to 1/48. Yeah, 64 to the 2/3 is 16. So 1/48. So we have a slope of 1/48. What can I do with that?
Do you plug it into the equation, the linear approximation equation?
What equation is that?
It's L of x equals f of x plus f prime of x times x minus x, or x minus a. Sorry, that should have been a.
So L of x equals f of x, and then I lost you.
Or f of a plus f prime of a times the quantity x minus a.
Right. So yeah, I mean, this will work. The way that we've most commonly done this, like in class, and the way that I've kind of explained it to people is, I mean, what I drew up here, we found the, basically we're looking for the tangent line to the curve at a certain point. And this thing here that I just wrote down may not look exactly like it, but that's what we're looking for. So what is f of a?
Four.
4, right? How'd you get that?
Cubed root of 64.
Right, so f of 64. Yeah, cube root of 64 is 4. We just found f prime of a as 1/48. And then a is 64. So basically this is our linear approximation, which we can simplify a bit. 4 plus 1/48x minus 64/48. What is 64/48? 4/3. So 1/48 times x plus 4 minus 1 1/3, so 2 2/3. So I believe this right here is my linear approximation. So as long as I pick x values that are close to 64, that approximation will be pretty good. So from here, where should I go?
Would we take the number we want to approximate now and input it into that
Right.
final? Yeah.
Yep, now that we have this linear function, we can do L of 64.1, which is equal to 64.1/48 plus 8/3. So basically whatever this value is what we want. And if I approximate it to 5 decimal places, I get 4.00208. And if I take the cube root of 64.1, I get 4.00208. So pretty good approximation for that far out. Any questions there?
So is a linear approximation just getting the tangent line, right?
Yeah, I mean, basically, so the short answer is yes. So if we look back to like 2 months, like probably like think of the first time I asked you to find the equation of a tangent line. You know, I gave you a function, I gave you a point, you found a derivative, and you use that derivative to find a tangent line. And then we probably just moved on, right? The only real difference between that and what we're doing now is what?
No idea.
So I mean, the only real difference now is, you know, in the past, we would have stopped here. Here's the straight line that is tangent to that curve at that one point. Now we're using that straight line to basically to make estimates about this function when I get away from that point a little bit. So if you're comfortable with finding tangent lines to curves, that is what this is. The thing that we're kind of tacking on now is you're finding the tangent line to a curve, and now you're going to use that line to say something about the function. So
I had a bit of a question. Like, I always wondered this. So, like, we take f prime of 64, but we're looking for the approximation of 64.1. So wouldn't that, is that where the error comes from?
That's where the error comes from. So I mean, you
Okay.
can't really, it's this slope is so shallow, it's hard to see it here, but one thing I'll say is this: the only point on this curve that is common to the straight line I drew is this point 64.4, right?
Mhm.
So as soon as I let x drift from 64, my linear approximation is going to be wrong. But it is going to be useful. It's going to be close.
So like, obviously, like in this case, 64 was the obvious value to use, but like,
Mhm.
how do you like, is there always going to be a, like a quote obvious answer or like an obvious number to start off with?
I either, I mean, two things that I can say to that. I either have to give you, I either have to tell you what the point is, or
Or it has to be something like this where there's a clear.
yeah,
to
or
the-
there
to
has to
the
be something
third
close by.
root.
Like,
Yeah,
I mean,
so like same thing with 81, you would know what that would be.
yeah.
Yeah.
I mean, you could have used 27 for this, but how good would that approximation have been?
Yeah, it wouldn't.
Right.
Yeah.
So, yeah, if I don't tell you what that base point is, kind of where you're gonna center that approximation around, I'm going to leave you a clear choice.
Okay.
Otherwise, I mean, otherwise there's no point in doing this. There's no point to have an approximation if there's not a good place to set your feet and make that approximation. For example, what is 5 cubed? 125.
Yeah.
So if I asked you to approximate like 90, I have no idea what you would use to approximate that.
Yeah.
You're so far from a logical perfect cube to make that work.
That makes sense.
All right. Anything else on this before I get a new screen? All right.
I have a question from 2.7.
Yeah, is that related to race?
I don't remember what this kind of problem is called, so I'll just, it's a particle is moving along a curve and passes through a certain point, and you have to find the rate of change between the distance of the particle to the origin at
Okay.
that instant.
So a particle moves at a constant rate
Along a curve.
along a curve.
Here's one that says y equals 4 square root 2x plus 3.
Okay.
Right, and passes through 312 with the x coordinate increasing at a rate of 2 units per second.
Passing through 312 at a
Increasing as a rate of 2 units per second.
in which direction?
It doesn't say. It just
Oh,
x
back up.
coordinate.
So back up to the 312 and read from there
Okay.
again.
Its x coordinate increases at a rate of 2 units per second.
Okay, so its x coordinate increases at a rate of 2 units per second.
Yep.
Its x coordinate.
Was this on the homework?
It was from the homework.
Okay,
Sounds
cool.
familiar, yeah.
That makes sense.
And the last bit it's asking is to find the rate of change of the distance from the particle to the origin at that instant.
Find the rate of change of distance.
From the particle to the origin at this instant.
Okay. Particles origin. Okay. All right, a lot going on. So What should we start with?
Labeling what we know,
What's that?
like clearly labeling what we know already and what we're trying to find.
Okay, what we know. So what do we know that's worth mentioning?
Uh, it it says just x coordinates, so is that just dx?
Not just dx. Dx is part of it. But let's be really specific. How does it tell you how does it tell you the particle is moving?
Dx dt.
Right. So, and what tells you that you have to look at the rate dx dt?
Per second, units per second.
Right. So units per second. So you know you have there's some kind of time base, some rate of change per unit time. What tells you I'm looking at the rate dx dt and not, something else?
Because it says the x coordinate.
Right. So dx dt is equal to 2 units per second. All right. Definitely a good thing to keep track of. What else?
Well, we want to find what dy dx is from, what is it, 0, 0 to 312.
Okay. Is that going to be dy dx?
What would that be, like what? A change in distance. So what, dd dx?
What's d in your mind here?
Distance.
Okay. Distance from where to where?
From origin to 312.
So let's draw a picture here. So we have a square root curve that's in general going to look something like that. Here's the origin that I want to find the distance from that point to wherever the particle is. So if I find that distance, how would I calculate that distance?
Pythagorean theorem, is it?
Pythagorean theorem. Yep. So yeah, and I think that's one of the more mysterious things about this homework problem is that you're not looking for dy dt or dy dx or dx dt. You're looking for something having to do with this distance that we'll call d. And since the x and y are perpendicular to each other, we can kind of set it up like this. So we know that constant rate of change for x in terms of time. We know we're looking at this distance. So can we give a name to the thing we're trying to solve for?
Is it dx over dy?
It's not dx over dy. So we're looking for a rate of change of distance. So that should tell you that, well, let's be more clear. The rate of change of the distance from the particle. So here's the particle, which really moves around, but we're kind of taking a snapshot of it as it crosses through this point 312. So we want to find the distance from the origin to that particle. More specifically, we want to find the rate of change of the distance from the particle to the origin. So we know we're looking at d something. So I'm looking for the rate of change of distance with respect to what?
With respect to x?
me see if it's more clear. Jezreel, can you read the last sentence of this question again? I thought
Right.
that it made really clear what we were looking for, and I don't remember.
It
hearing
was find the rate of change of the distance from the particle to the origin at this instant.
All right, this is from web work, right?
Yes.
Does it say what units it wants that answer in?
Well, in the solution, as a looking ahead, it looks like it wants dd over dt.
Right.
And yeah, units per second.
Right, but you know, did the question, the way it was originally posed, say units per second?
No.
No. Okay,
No.
I thought it made it clear.
Well,
But
I guess you can infer based on that
Wait.
x is in units per second, right? You can infer.
Oh.
no, that's not really good enough. Yeah, I mean, I thought that I remember, and maybe it didn't. I just can't remember what it is. But I thought there was something in the way the question was written that made it more clear that we were looking for DDDT. But now I'm not hearing it. And I kind of thought that, you know, when it was asking you for that rate of change, like next to the blank box was units per second, but sounds like that wasn't the case. So doesn't sound like it was terribly clear, but I'm telling you, the thing we're looking for is the rate of change of that distance, you know, from the origin to the particle with respect to time. Okay, so if that's the rate that I want, how can I find that? What do I need to set up to help me get there?
An equation that we can then differentiate.
Yep. So based on the kind of quantities we have to look at, we got to build an equation, right? So we want to find the rate of change of that distance. We know our equation needs to be based on distance somehow. What else do we know about the situation that we can say is related to distance?
Well, x's distance is increasing by 2 units per second.
Okay, so we know something about the way x changes. We want to know something about the way d changes with respect to time. So that suggests to me that we need to have an equation that somehow relates d and x. It can involve other stuff, but I think at a minimum, it needs to involve d and x.
Is it the Pythagorean theorem? Like just would differentiate that?
Yeah, I think that's a good place to go. And so we know something about this. Man, this horizontal distance is kind of, we actually know a lot about this horizontal distance, right? Because we know how far away, we know how long the distance we want to be. We know how long we want that distance to be at some instant. And we also know how fast that distance is changing constantly. So I think a good equation to go with, again, knowing that we want to relate x and d, is x squared plus y squared equals d squared. Because we don't have any rates yet because we're not there, but we know the rates, we know a rate we know is going to come from here, right? And a rate we'd like to know about comes from here. After we differentiate this, both sides of this equation with respect to time. So what would you like to do now?
Differentiate that and sub in what we know?
We could absolutely differentiate here. There's one thing that we could do to make things simpler on ourselves. Because if we differentiate this, what are we going to differentiate with respect to?
With respect to t?
Right. Let me give you a hint here. If I differentiate this with respect to time, we're going to get this: 2x dx dt plus 2y dy dt equals 2d dd dt. We know dx dt, right? We know we want to find dd dt. What do we know about dy dt?
Nothing.
Nothing.
So do we actually want to solve for D first? Because we know X and Y.
What do you mean we know x and y?
Well, because right now X is 3. Wouldn't the distance between the origin and where the point for X be 3, and then for Y it'd be 12? So we can do.
Here's the thing to be careful of. If you just sub in 3 for x now, then what you're basically saying is that x is always 3,
Okay.
which is not true. I mean,
No. But at this
so
instant,
this
it is.
this picture I drew is it's a snapshot of something taken in time, right? But that doesn't mean, so just like when you take a picture, does not mean the thing you took a picture of was not moving. We were just interested in it at an instant in time. So really this particle is moving at a constant rate to the right. So because of that, I can't just call x3 and y12 in this equation, because that implies that they're constant things, and they're not.
Would we take the derivative of the equation it gave us, y equals 4 square root 2x plus 3 with respect to time?
Wait, can't we call Y that equation?
Yeah, that's what I was
Okay.
getting at. And Jezreel, I think you were very, very close to, because essentially what we're going to do is, we don't know anything about dy dt, which is what really makes the thing that I scribbled out a nightmare to deal with. But because I know exactly how y and x are related, I don't actually need to. So what I'm going to do is this: d squared equals x squared plus, would you agree this is all y?
Yes.
So then I get d squared equals x squared plus 16 times 2x plus 3. So d squared equals x squared plus 32x plus 48. So yeah, using the information I had, I got away from having to deal with y directly. Because if I have x, I know everything I need to know about y. All right, so I have this equation that, I said at a minimum I wanted it to deal with d and x. Now that's all it deals with. So this is an easier situation to be in. So now that I have this equation, what can I do with it?
Would we
Now you
need to
can-
get rid of the
Now you can
square?
differentiate.
So I heard something, I think, yeah, so I heard someone say differentiate and someone else said
Get rid of the square on D.
Oh. you could do that. The only caution I would, so since this is true, this is also true. D equals the square root of x squared plus 32x plus 48. Could you differentiate both sides of this with respect to time?
You could, yeah.
The only reason I might not want to do that, especially if you're in a situation where time is important, the time you have to finish. On the right-hand side, you're looking at a chain rule and the derivative of square root. I think I would rather, before I move on, I'll say that both of these absolutely will work. It's just, I think for me, it's kind of a matter of two things. Dealing with a simpler derivative and time management. So if I take the one on the left here and differentiate with respect to time, I'll get 2d dd dt equals 2x dx dt plus 32 dx dt. And that's it, right? Do I know enough there to solve for dt. Do I know what x is in this situation?
Yeah, x would be 2.
Not x.
3.
X is 3. Dx dt is going to be 2. The only kind of missing piece here we have is d. Do I know what d is equal to at this instant?
If you use Pythagorean theorem, right, you could
Right.
find it. Yeah.
So I know that, yeah, the x distance is 3. Was it 312?
Yes.
Right. So basically what you have is this 3 squared plus 12 squared equals d squared, which is equal to 9 plus 144. So that distance is radical 153 equals 2 times 3 times 2 plus 30. What did I just dropped the thing I want to solve for? So 2 radical 153 dd dt is equal to 2 times 3 times 2 plus 32 times 2. So whatever this comes out to be is your approximation for what that rate is. Any questions there?
Yeah, could you explain the canceling for me at the very end there?
Yeah. Basically what I realized is that I should erase that as well.
Thanks, Professor Ruiz.
Yeah, no problem. So from here, yeah, so in order for me to solve for this rate, I'm going to divide both sides by 2 radical 153 to isolate dd dt. The thing that I noticed here is that in the numerator here, I can factor out a 2 from this left-hand term and this right-hand term, right?
Yes.
Basically what I did was this, and I did it quickly. So factoring out that 2 allows me to just cancel it out in the denominator.
So d dt would essentially be 6 plus 32 over root 153.
Yeah. Comes out to be a little bit more than 3. 3.072.
Thank you.
I had a question in the chat to do a, is it a normal line? Finding a normal line? Oh yeah, finding a normal line. So let's do that.
I just had a quick question about the structure of the test. Like, is it gonna be more unit 2 or unit 3 or about the same or?
I mean, just by the amount of time we've spent on stuff, I would expect more stuff from unit 3, but it's not going to be overwhelming.
Okay.
And it is that, yeah, it's not going to be like all that lopsided. And also kind of a hard question to answer because, for example, what was section 2.4 about? Product and quotient rule?
Yeah,
section
but
2.6
that's kind of in everything.
Yeah, I mean, and section 2.5 is chain rule. We've kind of dragged that stuff into everything we've done since. So
Mhm.
yeah, they aren't really all that independent from each other.
Okay.
Okay, normal line stuff. Unless anybody has anything specific, I'm going to try to cook one up that doesn't behave too badly. Let's say I have this function, f of x equals arctangent of e to the x squared. Find normal line at x equals 0. All right. I think this will work. So what do we do with this thing?
What is the normal line supposed to be again? That's not a derivative, is it?
It has something to do with the derivative. So let me draw a schematic here. Let's say I have a curve. You know what a tangent line is, right?
Right, yeah.
So we'll call a tangent line T. The normal line is this thing, which is perpendicular to the tangent line. So you're still required to think about a single point when you're dealing with this kind of thing. Okay. So you still have to think about a single point, but instead of looking for this line that kind of touches but does not go through the curve, you are looking for this thing that's perpendicular to that. So given that, what do we have to do?
Well, first we'd have to find the derivative, right?
We need
of-
we need a derivative. So we got to find the derivative of this function I threw at you. So how do we find the derivative of, how should we set that up to help ourselves?
Chain rule,
Chain rule. Why?
because arctan is going to be your inverse tangent, and that's going to be your outside function, and then your inside function is going to be e to the x. Oh gosh, are there two chain rules happening inside
Yeah.
that?
So
Okay.
so
I recommend
believe you're
first
right that
finding the inside. First finding the inside and then plugging that in to the arc.
okay.
Tamp.
And I don't know if I've done this in class. I think I have, but there's nothing about chain rule that says you have to be limited to two functions. So yes, I believe the outer function is arctangent. If we go one layer inward, what's the next function going to be?
e to the power of x.
E to the power of x. And then I'm going to go ahead and set this up for one more layer, because what's the last function going to be?
X squared.
X squared. So let's define this. This function is actually a of b of c of x, which is fine. So from here, now that I've kind of defined how this function is built in terms of smaller, simpler functions, how can we find that derivative?
Would we take the derivative of each function working backwards from the center?
Yeah, so I mean, really, we do need them all individually. So we'll go ahead and do that. What's the derivative of arctangent of x?
1 over x squared plus 1.
Yep, 1 over x squared plus 1. How about the derivative of e to the x?
E to the x?
And x squared.
Two x.
2x. Okay, so I have all the individual derivatives. Can I use that to give the derivative of the overall function then?
Would it be the a prime function first?
So yeah, we're going to go from the outside in. A prime, but
But you would replace the x in that function with b prime?
not b prime.
Just b then?
So b of x,
B of x.
not quite. So let's do this picture here that I've done before. What's the first thing that happens to x here? A, B, or C?
C.
C. So the first thing that happens to this function is, or to this input x, is my innermost function, which is called C. And what comes out of there is x squared. Then it goes through what next? B. What comes out of there?
E to the x squared.
E to the x squared, yep. So that becomes e to the x squared. And then finally that thing goes through A. What comes out of there? That's the arctangent of whatever came in, right? So when we take these derivatives, we kind of have to work from the outside back inward. So the derivative of function A. So we need the derivative of A, but what is the input to the function A in this, organization that I've done here? It's not actually X,
Is it e to the power x to the power 2?
right? Or in the language I'm going to use right now, it's actually B of C of X.
Yeah.
Yep. But yeah, you're right. So that's the first layer of the chain rule. What's the next layer going to look like?
The derivative of b of c of x.
Right, the derivative of B, but what's the input to B? It was actually what came out of C. And then the final layer is going to be C prime of X. So now we can actually fill in the specific pieces of our function. A prime was 1 over x squared plus 1. So I should call it 1 over e to the x squared plus 1 times b prime, which was e to the x, except that's going to be e to the x squared. And then the final piece is going to be c prime, which is 2x. So our big nasty derivative is 1 over e to the 2x squared plus 1. Actually, I'm going to consolidate it faster than that. All right. So that is the derivative. Any questions there? I kind of threw a nasty function at you on purpose. All right.
And that's just the final answer then, yeah?
No, that's just the derivative. So remember, this whole thing was about us finding the normal line.
Oh, at 0.
So I want to find a normal line at that point. How can I use the derivative to do that?
Plug in 0 into the derivative.
Yeah, let's plug in 0. So I get f prime of 0. And I'm just about to learn that this doesn't work. So 2 times 0 times e to the 0 over e to the 0 plus 1 comes out to be 0 over 2, right?
So is your slope just 0?
Well, the slope of the tangent line is 0, right?
Oh yeah.
So
Which
then
means you have a straight line,
what kind of a straight line?
horizontal straight line. So there's going to be no perpendicular to it.
Right, so yeah, the tangent line is horizontal, which means the normal line would be vertical.
Vertical.
So can I cheat now? Can I give myself a different x value that will actually work without being really terrible?
Would 1 be?
Yeah, it's gonna spit out some ugly numbers, but we'll do it.
Oh,
So let's do x equals 1.
oof, sorry.
No, I mean I did this to myself, so we're gonna live with it. So f prime of 1 is gonna be equal to 2 times 1 times e over e squared plus 1. So 2e over e squared plus 1. So this is the slope of the tangent line, right?
Yeah.
So then what is the slope of the normal line? How
Would you
are
have
the
to-
slopes of perpendicular lines related?
Are they the inverse of each other?
What do you mean by the inverse?
What would be to the power of -1 in notation?
Not quite.
Is it just
Reciprocal then.
yeah?
Is it what?
Negative reciprocal.
It's the negative reciprocal. So what's that going to be in this case?
Negative e squared plus 1 over 2e.
Yep. So that is the slope of the normal line. So we got the slope. How do we keep going?
Could we use either point slope form or the other one?
Yeah, so we use, the two tried and true ones that people like: slope intercept and point slope. We know the slope. I gave you an x. Do we have a y value?
We could if we input the x value into the original function.
Right. And this is where it's going to get somehow even uglier. So x equals 1 means the y value you're going to get is the arctangent of e, right? So if it pleases everyone, I think I'm going to stop here because I think this has been a good reminder of kind of a nasty derivative that touches a lot of things you're almost certainly going to see tomorrow. And at least kind of going over what the scheme is for dealing with a normal line. So if you're comfortable with finding a tangent line, and if you're not, I would really brush up on that a little bit before tomorrow. But the only real substantial change from finding a normal line, or from between finding a tangent line to finding a normal line, is the fact that you are dealing with not the slope of the curve at a point, you're dealing with that perpendicular slope. Anything else about this one?
Did you say we're gonna see like finding a derivative of something like this tomorrow?
I'll go ahead and tell you that I think there's no way I could expect you to, on one question, do this kind of thing. But you can pretty much know for certain that you're going to see all of these things tomorrow. If not at once, you're going to see them all. Does that make sense?
Yes.
Really quick question about inverse trig.
Mhm.
Do we need to know the cosecant and secant, or the what is it, is it cotangent?
For the inverse,
Yeah.
like inverse cotangent,
Mm-hmm.
no, I'm not worried about those things.
Okay, so just sine, cosine, and
Yeah, I
tangent.
mean, stick with the fundamental three.
Okay.
But yeah, I mean, I don't know if I've seen the arc cosecant of something since calculus 1. It's
Okay. Just
yeah,
wanted to be sure.
let's just, yeah, we'll stick with the ones that are the heavy hitters, the ones that really make themselves known.
Mm-hmm. Got it. Thank you.
All right. If there's nothing else about that, I'll get a new page. Who else has something?
For the last question that we just did, are you just supposed to know that arc cos or arc tan is 1 over x squared plus 1? You're supposed
So
to memorize?
I suspect that before long, let's look at arctangent. Y equals arctangent x. This is here's the best case scenario. You know this. Here's the second best case scenario. You don't remember it, but you can rebuild it. And what I mean by rebuilding it, and I think I did something like this, but I don't think it was for tangent. But here's what you can do, and it'll take you a little longer, but it's better than not getting there. If I know that y is equal to the arctangent of x, I know that x is equal to the tangent of y. That's just something that comes from inverse functions and how they behave. Then from there, I can take a derivative of both sides with respect to x, and I get 1 equals, what's the derivative of the tangent function? It is secant squared y, and the derivative of y is dy dx. That means dy dx is equal to 1 over secant squared y, which is the same thing as cosine squared of y. So where can I go from there? I can draw this triangle here. And here's how this triangle is going to be built. It's going to be based on this idea here. If x is the tangent of y, I'm kind of saying that y is an angle. And if the tangent of that angle is x, that means the opposite over the adjacent side are x and 1. And Pythagorean theorem tells me this hypotenuse has to be radical 1 plus x squared. And then from there, what is the cosine of y? should be adjacent over hypotenuse, 1 over radical 1 plus x squared, all squared, and that's equal to 1 over 1 plus x squared. So just to reiterate, I mean, just in terms of managing your time, it would probably be best if you just knew this, but you know, if something happens, you don't get a ton of sleep, or you just kind of lose this on the day. Here's something that might help you get to where you're trying to go. And I mean, I think when I did this in class on Monday, or maybe it was last week, I did it for arc sine, but yeah, you can do something similar for any one of those 3 inverse trig functions. All right, anything else?
I have a question about error, like the difference between propagated error and relative error.
Propagated error?
That's one question that I've gotten before. I've gotten like stuff where it's like find the propagated error and then find the relative error.
Oh, okay. Yeah, propagated error is not something I've used in class, but that's
Okay, it was on WebWorks and it like kind of threw me off, but
yeah, the difference between that and the relative error is, if you have an example, I think it'd be easier for me to explain the difference if we looked at a concrete example.
yeah, I'll look one up. Someone else can go while I do
Okay.
that.
If we could go over L'Hopital's rule once more.
Yeah. Got an example?
Limit as x approaches 1, 5x minus 5 over x squared minus 1.
Limit as x approaches 1 of 5x minus 5 over what?
Wait, 5 to the power of x and then minus 5.
Over?
X squared minus 1.
Okay, so what's the first question I should, or what, yeah, how can I start looking at this thing?
We would need to know the individual limits of the numerator and denominator.
Okay, what are those individual limits?
I think the top is 0.
So yeah, 5 to the 1 is 5, 5 minus 5 is 0. How about the denominator?
It's also 0.
So we got this form 0 over 0. What does that tell us?
That we can use L'Hopital's rule.
Yes. So
Okay, well,
because
that's
we
fine.
have that indeterminate form 0 over 0, what's the other one that allows us to use L'Hopital's rule?
Infinity over infinity.
Infinity over infinity. So because of that, this thing is equal to the limit as x approaches 1. So by virtue of L'Hopital, what other limit can I look at instead?
What was it? The derivative of each numerator and denominator?
The derivative of the numerator over the derivative of the denominator. So what is the derivative of 5 to the x minus 5?
5x to the power of x minus 1 over 2x.
So it sounds like you're doing power rule for the numerator, which is not how to handle that kind of function. So there's a difference between the way you handle x to the 5th versus 5 to the x.
Oh, it was 5x times the natural log of 5.
Yep. Okay. So 5x times natural log of 5 over 2x. Is this a limit I can deal with?
Yes.
Right. So what's the limit then?
I think I need the calculator for this because I can't remember the natural log. I had to deal with that in limits.
Well, what kind of thing is natural log of 5? The natural log of 5 is just a constant. So this limit is just 5 natural log of 5 over 2. So that should be that limit. And basically what's going on with L'Hopital's rule is, you know, the base point x equals 1. As x goes to 1, the numerator goes to 0 and the denominator goes to 0. So what we're really looking for is, all right, they both go to 0. How fast are they going to 0? So that's why the derivative is, that's why we can look at the derivative of the numerator and derivative of the denominator. Get a little more information than, well, they're both going to 0, but they aren't necessarily both going to 0 at the same rate, in the same fashion. Now, Brendan is asking, is the test basically going to have a question from each unit? Not really. I mean, like I said before, a lot of these things build up on each other. So, you know, for example, in terms of the scope of the sections on this test, so from 2.4 to 3.7, the earliest thing that'll be covered on this test is going to be product rule and quotient rule. But we have used those things in every section that's followed. So, yeah, the things we've done since the first test haven't really been all that independent from each other. They've kind of been spiraling and stacking on top of each other.
So it'll just be questions that incorporate everything we've had since
Yeah.
the first exam. Okay.
Yeah, pretty much. I mean, for example, I could, if I ask for a derivative of a function like this, I mean, that's quotient rule, product rule, chain rule, which are all chapter 2 things, but it's also, I'm also having you look at exponential functions and log functions, which are things we dealt with in chapter 3. So it's a little hard to say. I mean, I can't tell you what one section covers that. So, yeah, I mean, basically, there's a lot of unity between the things we've talked about since the first test. Isabel, were you able to find something?
Yeah.
Okay.
So it doesn't have propagated error, but it's the maximum error in a calculated area of a disk. And
So the area of a disk. All right.
so the radius of a circular disk is given at 24 centimeters with maximum error in measurement of 0.3 centimeters. Use differentials to estimate the following, which is max error calculated and then relative error.
Okay. Use differentials to calculate max error and max relative error.
Yes.
Okay. To answer the question that you first asked me, this thing right here is propagated error. Basically, if you don't know, the word propagate means, you know, it basically the error that results from the error that comes from your measurement. So to propagate something is to basically consequences that happen later because of this thing that happens initially. So when I measure the radius of this disk, I measured it at what I believe is 24 centimeters, but there's an error in my measurement of possibly 0.3 centimeters. That is going to propagate to an error in area. So first answer is that these two things are interchangeable: maximum error and maximum propagated error. Those are the same thing. Having said that, I don't think we've talked about one like this tonight, so I would like to finish this. So how do we proceed to find these two errors they're looking for? I'm going to go ahead and find percent error as well.
That was actually part of the original question, but I left it out.
Gotcha. All right. So how would we find these three things?
Well, we would use the area of the circle to relate all of them.
Right. So area equals pi r squared.
And our radius is 24, but our max error is going to be 24.3 because it's the maximum.
Right. So that'll give you a maximum area, right?
Mm-hmm.
But that is not using differentials. So
Oh, I totally forgot about that.
yeah, what does that mean? What is a differential? How do we get those involved?
Would we have to include something like time in order to take a differential in respect to it?
Not really, because time is not an issue here, but
Well, maybe not time, but we have to add something else to take respect to for the
Yeah.
differential, right?
yeah, so we need a derivative, right? So let me ask this way. By definition, a differential is related to a derivative.
Mm-hmm.
So what should I take? I want to take a derivative of this function we wrote down. What should I take the derivative with respect to? So what variables should I base that derivative on?
dA to dr?
Right. So really what I have here is, and to make it even more clear, area is a function of radius and is defined as pi times radius squared. So I can take this derivative, dA dr equals 2 pi r, right?
Mm-hmm.
And basically what I'm going to use differentials for is I can approximate a change in area that results from a change in radius. And we've already been given what that change in radius might be, right?
Yes, that
Right.
would be the positive 0.3.
Right. And really, positive and negative doesn't really do much other than tell you you're looking for the maximum error.
It's asking for the maximum.
Right. Well, the maximum error.
Oh, it's like, okay, no, I get it now. Okay.
Yeah, it's not the maximum. It's not the maximum possible area they're necessarily asking for. It's just how wrong might you be, and whatever answer we find, we could be that wrong as an overestimate or an underestimate.
Got it.
So for us, that would be dA equals 2 times pi times, we believe the radius is 24 centimeters. I could be wrong by as much as 0.3 centimeters. So that gives me 14.4 pi centimeters squared. So let's actually go ahead and approximate. So 14.4 times pi equals 45.24. So 45.24, that's our maximum propagated error, or maximum error, whatever the exact language they used. Because of this, because of this possible error in the measurement that I can actually control, that results in a calculated error of 45.24 cubic or square centimeters that might result from that. We okay on that first part?
Yes.
Okay. What's the difference between that and the relative error?
Is the relative error over what would be the correct error?
Right. So basically, that 45.24 centimeters squared, I have no idea how significant that is. It might be really bad. It might be totally reasonable. To have a better idea how to get that, I want to compare that. I want to compare that to what I believe the real value is. Like in a perfect world, if I was able to measure this exactly, basically I'm trying to find that ratio. So our max error is what we just found, 45.24 centimeters squared. How would I find the nominal value in this case?
Find the area with just a radius of 2.4. 24, sorry.
24, yeah, okay, just making sure it's 24. So yeah, we're just finding, yeah, basically we're assuming we're totally right. So the area given a radius of 24 centimeters is pi times 24 squared, which is 24. So 1809.56 centimeters squared. All right, and I am getting this number for the relative, 0.025.
Yes.
Right, so that is the relative error, 0.025.
And then percentage error is just taking that and multiplying it by 100.
Right, so the percentage error is basically converting that decimal quantity to a percentage. So 2.5% gives me a lot better of an idea as to how significant that error in measurement is than 45.24 centimeters squared. If the only information I had was that, then, well, was the original disk 12 centimeters or was it 24 meters? Because in one of those cases, that error is a lot more significant than the other. But the purpose of having that percentage error or the relative error gives you a better idea as to how well controlled this thing is. All right, any more last minute questions?
Yeah, is there gonna be, there was that one triangle question, something about the shadows, the lamppost, and the woman that was, is that something like that gonna be on the exam?
And that's probably a little more than I can I can reasonably ask for related rates. So look, I'll just kind of let you behind the scenes a little bit. There's a lot of stuff that I need to make sure you all understand on tomorrow's test, and it's not doing any of us any good if I if I had you spend 20 minutes on a related rates problem.
Okay.
So yeah, I need to make sure you understand how to deal with those things.
But
It's not good for any of us if I really load up on it. So what I would focus on with the related rate stuff is, as I kind of said this in class, but I think it's worth repeating. We looked at a lot of examples, and those examples look very different in a lot of ways, but also the way you approach them and organize them and the things you have to keep track of, those things are pretty standard across the board. Like, you need to know what variables you're looking at. You need to have some kind of an equation that joins the variables you care about, and specifically the things you know and the things you need to find out, the things you need to solve for. Hopefully, I think I'm going to guess that you all know that a derivative with respect to some quantity, which has probably always been time. I don't think we've had an example where the governing variable wasn't time. But you know you're going to have to deal with some kind of a derivative. And then basically using your differentiated equation to solve for whatever unknowns you have. So again, we've looked at a lot of different examples of related rates problems, but they all kind of you can kind of approach them using a similar set of tactics. Jaylene is asking, is there going to be a problem that requires the triangle things? So yeah, I mean, since we did some inverse trig stuff, you may have to evaluate some of those things exactly. Like if I ask you what the arctangent of 1 is, or the arcsine of -1/2, things like that, you may have to find those exactly. So again, I think memorizing the unit circle is kind of the time you would spend doing that is not worth the benefit you might get from it, but kind of realizing the patterns that happen. One thing I would really emphasize for the inverse trig stuff is if you're looking for the inverse sine or the inverse cosine of some measurement, make sure you know what angles are inside the range of that function. And what I mean by that is, if the arcsine, if I take the arcsine of some value, that angle has to live in one of two quadrants. And it really is important to know what those quadrants are, to know what the what the range of all those functions are. Yogesh is asking what the scope of the test is essentially. No chapter 4 stuff. So yeah, from 2.4 up through the end of chapter 3 and no further. All right, 4 more minutes. Oh, okay. Yeah, you're welcome. All right, I think I have 9:04, so I'm gonna go ahead and log off. But I will see you all tomorrow.